Hello, everyone. It is our honor to introduce our work on this platform. Today, we would like to introduce our study of artificial intelligence-enabled radio propagation for communications. The part 1 of this work focuses on channel characterization and antenna channel optimization. This invited paper is finished by the authors from the affiliation given on the slide. This invited paper includes 4 sections. In Section 1, we introduce the development history of artificial intelligence and machine learning, and the application of machine learning to propagation channels. Then, the machine learning-based channel feature extraction methods are presented and compared in Section 2. Next, the AI or machine learning-assisted optimization and modeling for antenna design, which aims to improve the radio propagation. Finally, some important issues and challenges are discussed in Section 4. For the channel feature extraction methods, we first review the traditional channel parameter estimation methods, such as Bartlett beamformer, music algorithm, SAGE, and so on. Then, we investigate the machine learning-based estimation methods, such as SVM, artificial neural network, PCA, RVM, and so on. All the algorithm has been listed in Table 2. In addition, as an important part of channel feature extraction, MPC's cluster identification methods are summarized. The key ideas of 4 typical clustering methods are given in Figure 2, which are shape-based, optimization-based, distance-based, and density-based cluster identification algorithms. For time-varying channels, the MPCs not only need to be clustered but also need to be tracked. Therefore, some tracking algorithms are presented in the overview. By combining the tracking and clustering, a new solution is proposed, which is trajectory joint clustering. It tracks MPCs first, and identifies the clusters based on the trajectories. In this case, the clustering and tracking process can make up for each other, which results in a fairly good tracking and clustering accuracy. Machine learning is useful to address this optimization problem due to its ability to create mathematical models for the complex problem involving myriads of antenna and channel parameters. Different from the use of machine learning to speed up parametric optimization in classical antenna design to obtain the detailed antenna properties, the focus of this survey is on optimizing the far-field properties of antennas for improved interaction with the propagation channel and thus enhanced system performance. Finally, some challenges are discussed in Section 4, which can be considered as guidelines for future ML-based channel analysis and modeling research. The details can be found in the paper. At last, on the behalf of the authors, we would like to thank the IEEE Antenna and Propagation Society to give us this great chance. Many thanks again.
Hi, this is a short introduction to our work on a general method for calibrating stochastic radio channel models, that is, fitting the parameters of stochastic radio channel models to data using kernels. The state-of-the-art calibration method goes as follows. Let's say you start with a bunch of radio channel measurements, Y, and then you extract the multipath parameters, such as the delays and the gains, using some high-resolution algorithms such as music, SAGE, or Esprit. And then depending upon whether your channel model is cluster-based, then you would fit a clustering algorithm to find its cluster parameters. And then once the multipath components have been clustered, then we fit the parameters of the channel model using maximum likelihood or least squares fitting. And in the end, we get a point estimate of the parameters theta of the channel model. The problem with such an approach is that at each step, we are required to implement a sophisticated algorithm such as the music SAGE or these clustering algorithms that themselves have a number of hyperparameters to tune. And the overall performance of the calibration method is unknown, although we might know the performance of each of these individual steps. Another problem is that such an approach is tied to the kind of model that you use. So if, let's say, you propose a different modification to a channel model, that means the calibration pipeline needs to be adjusted accordingly. And so there is no one method that you can use to fit different channel models. As a result, it's very difficult to compare different models on the same data set. What we propose is to use easy to compute general summary statistics of the data instead of going the multipath extraction and clustering route. So we compute these log temporal moments of the channel responses like this, and then use these to fit the model using our kernel-based approximate Bayesian computation approach, which is described in the paper. And in the end, what we get is not only a point estimate, but also a characterization of the posterior. So the uncertainty is also characterized in our approach as compared to the state-of-the-art method. So what we find is that we used this approach to fit the Saleh-Valenzuela model and the propagation graph model to 60 gigahertz MIMO channel measurements. And here the channel measurements are in black, and then the two models are in blue and red. And here is the power delay spectrum, the RMS delay spread, mean delay, and receive power, which have been plotted for the fitted models. And we see that our method is able to calibrate both these models to the data, and then without the need for any multipath extraction or clustering. And these models have very different mathematical structure, but they're still calibrated in the same way, which means that now we can compare the fit of these two models and make decisions based on which model is better suited for the data at hand. Thank you.
This video will briefly introduce our research on virtual antenna array with directional antennas for millimeter wave channel characterization. Here we briefly review two popular channel sounding schemes. The first one is a directional scan sounding. We employ a directional antenna and fix it on a mechanical rotator. As the rotator rotates, the directional antenna could capture the signals from different directions. This sounding scheme is widely adopted due to its simple setup and convenient implementation. However, the angular resolution is limited by the main beam width of the directional antenna, and some antennas could also have high side lobes, which might introduce errors in parameter estimation process. Another popular sounding scheme is the virtual array-based scheme. In the conventional virtual antenna array-based sounding, a single omnidirectional antenna element can be moved to different spatial positions, forming arbitrary array configurations. To easily compare with the directional scan sounding, we use a virtual uniform circular array here for illustration. The channel spatial profiles with high angular resolution can be obtained by using array signal processing algorithms. For millimeter wave and sub-terahertz band channel measurements, using low-gain omnidirectional antenna is not favorable, and the required omnidirectional antennas in these bands are scarce. What we propose is a hybrid channel sounding scheme which combines the advantages of the previous two methods. That is a directional antenna-based virtual antenna array framework. The proposed method can further improve the angular resolution and suppresses side lobe effects compared to the directional scan sounding. The high-gain antennas are used instead of the omnidirectional antennas, which are more available and favorable in high-frequency bands. Due to the slow mechanical movement speed, the two reference methods and the proposed method are typically used in static environments. Along with the proposed sounding framework, a modified classical beamforming is also proposed to support the signal processing procedure. A window function is introduced when calculating the array weights. By properly selecting the size of the arrays and window functions, high angular resolution and low side lobes can be achieved. We have validated our idea firstly in an RF clean environment like the anechoic chamber. The power angular delay profiles obtained using two reference methods and the proposed methods are compared. We can see that the proposed method can significantly improve the angular resolution and suppress the side lobes in spatial domain. The second scenario is a typical indoor office. We have estimated the multi-pass parameters using three methods. The results further demonstrate the effectiveness of the proposed sounding scheme. Please refer to our paper for more details and feel free to contact us if you have any questions and comments.